Okay, hello everybody. Thank you for joining May's Southeast Regional Group presentation. Today we are joined by Stewart Agar from the Department of Civil and Environmental Engineering, Imperial College, London, and he's going to be presenting on the developments and innovation using InSAR. So I'll pass over to you, Stewart.
Thank you very much. Yeah, thanks for having me. You might know that there was meant to be a talk on the Harwich Formation today, but Justina couldn't be here, unfortunately. So I hope you'll make do with me. I'll be talking about Interferometric Synthetic Aperture Radar, which is a relatively new and quickly developing system in order to measure ground deformation. I'm particularly focusing on satellite-based InSAR, and talking a lot about the work that our wider team is doing to really advance the applications of this technique to engineering geology applications and some new applications that you might not have heard of previously. So yeah, I should probably just say that I'll be presenting a lot of work from the wider research team. So I'm sure they would like to thank all the sponsors that have supported them materially and through data, and yeah, it wouldn't be possible without all the sponsors. So I'll just go through the presentation outline. I'll introduce the team. I'll talk a little bit about a specific type of data processing called persistent scatterer interferometry, and that's been widely used now for maybe 20 years, and it's finding increasingly valuable applications, especially in infrastructure monitoring, but hopefully I'll show a lot of applications of PSI in geology and engineering geology as well. I'll then talk a little bit about my work using distributed scatterers, and that's really trying to improve the performance of InSAR in rural areas, specifically in the UK. But in general, PSI, it encounters difficulties when there's vegetation covering terrain. Also some issues with soil moisture, and my work has tried to really separate out these components, and in order that we can get better measurements of ground deformation in rural areas. I'll then speak a little bit at the end about what we think some really exciting future work for InSAR, and how we can particularly downsize that and mount it on a UAV, giving us the flexibility to monitor much smaller assets and much more otherwise hard to measure phenomena, such as changes in moisture content of soils and things like that. So please let me know if my internet connection is being a bit tricky, because I can change that if needs be. Sorry to if that's an issue. I'd just like to introduce the team first. So our supervisors are Dr. James Lawrence and Dr. Philip Mason, based at Imperial College. And we're also supervised by Professor Richard Gale, who's now at Royal Holloway University. So I focus on improving InSAR for rural areas. I'm also going to be presenting work from Jenny Schooler, who's just handed in her thesis, and she's focused on specifically the Thames Tideway Tunnel in London, but more broadly in validating InSAR results using things like corner reflectors, which I'll introduce at one point later. Gosia is looking at coastal processes such as erosion and cliff stability issues on the coast, and is the main man behind developing these UAV-based InSAR systems as part of the team. And we've also got some of Zishao's work, and he's looking at GDF siting, particularly in China, and how he can use InSAR to really help with the site characterization stage of siting a GDF. Sorry, that's a geological disposal facility for radioactive waste. So using InSAR to characterize the long-term performance of the rock. So just so we're all happy with what we're talking about, I'm focusing on satellite InSAR. So we're using these synthetic aperture radar satellites, and particularly Sentinel-1 is a real great source of data. So these are European Space Agency satellites, and all the data is made available for free online at point of use. So you can register today if you're not having your dinner after this talk. You can log on online and register and start downloading the data. It's very accessible. So it's at the moment 2 satellites which are in opposing orbits, and they both image, for instance, in the UK, the same area of the UK every 6 days from the same orbital track. So that gives you a really long time series of data, quite temporally high temporal resolution in terms of every 6 days going back to, I believe, 2018. We've got, was it 2016, sorry. We've got a real wealth of data from these satellites, all available for free. Just to talk about the main principle of InSAR, we'll be sending out a sinusoidal radar signal from our satellites, and we'll measure the return of that signal. And basically on the timing of that, we can determine the range of an object. If we then, if the satellite then goes back around the Earth, and in between there's some subsidence, for instance, or a translational slide here of this house. The next time we measure this radar backscatter, we'll detect a very different range, and using the difference in timing of the signals that we measure, and particularly this change in the phase of the signal. So that's the timing of the peaks and troughs of the sinusoid. By looking at the change in phase here, we can infer that as a change in range. There's some other potential causes of a change in phase. It's obviously a little bit more complicated than just taking two numbers from each other, but the basic principle relies on this proportionality between the phase and the range of objects on the ground, which we call scatterers. So InSAR really came into the limelight with this image of an earthquake on the left here. So this is what's called an interferogram, and it's showing the with the color axis of this this image, it's showing the change in phase between two images in this case. So because this is the Landers earthquake in California in '92, I believe, and there was meters of movements, you're getting a lot of change in phase essentially, and you can relate that directly to the change in position of the ground, the scattering objects on the ground. Since then, we've got newer satellites and more data, and particularly with, for instance, Sentinel-1, when we've got years of data available, we can look for much smaller changes in phase and consistent changes in phase in order to measure consistent, very small, small magnitude displacements of objects and infrastructure. For instance, this is Blackfriars Bridge here, and this is a bit of work by a previous student in the team who's since got a PhD and gone on to Trail to Mirror. So this data is showing that the bridge is actually deforming by around, I believe it's 2 millimeters per year. And these small displacement rates can be measured very accurately when you've got a lot of images. So accuracies of 1 millimeter or less are very typical when you've got a good amount of time series data to analyze. The typical spatial resolutions in terms of the separation of points that you measure, they'll be about 3 meters by 14 meters, something like that for Sentinel-1. You'll get a bit of variation depending on where exactly in the world you're looking from and where the satellite is at one time. But those are typical. You can get high resolution data from different satellites, but normally they're commercial, and there's normally an extra cost involved if you want to do that and get high resolution data. So as a result of these impressive accuracies and the quite good spatial resolutions, there's a lot of valuable applications of InSAR, and hopefully I've got some on the next slide. So this is again work from Christine. This is showing with this red line here. I'll get my pointer up and hopefully you can see my pointer. This red line snaking across central London here. This is the Thames, this is Hyde Park. This red line is Crossrail and the tunnelling associated with Crossrail. Because of that tunnelling, there's been around 2 millimeters per year of subsidence above the route of the tunnel between the years 2011 and 2017, for which this data applies to. You've also got, hopefully you can see, there's a bowl of subsidence here. I've got something in the way on my screen. Sorry, I've got rid of that now. You've got this bowl of substance here near Canary Wharf, and that's associated with a lot of dewatering activities for building these stations, I believe, associated with the Crossrail projects. And that's being measured as a result of extracting groundwater. You're getting this subsidence. With this blue splodge, as I call it here on the left, these measured uplifts, that's associated with the Northern Line extension, which actually finished dewatering before this set of data was taken. So as a result of the dewatering stopping, the ground began to rebound over the period of imaging, and you get this roughly 2 millimeters per year uplift effect in opposites to the subsidence that we've. I'll just move on. I'll just talk quickly about persistent scatterers. So a scatterer, hopefully mentioned before, is any object that's responsible for a measurable echo that we can measure with the sensor on the satellite. So a persistent scatterer, by that logic, is something that's going to give us a stable measurement of its reflectivity. So that's a stable measurement of its phase, as well as its the signal strength, which is called the amplitude. So in order to identify these persistent scatterers, we look for the noisiness in its amplitude. So that high signal to noise in amplitude is going to be, if we do a bit of maths, we can show that that's going to equate to a reliable phase as well. So the phase is what we use to measure the deformation, but the strength of the signal being measured, that's going to be a useful proxy in order to basically predict beforehand how accurate each point is going to be. So by picking out these persistent scatterers, working out where they are, we can account for a lot of the other potential sources of error in our InSAR data processing. And as a result, we get these very accurate, millimetric accurate often measurements for wherever a persistent scatterer is present. If we don't have any persistent scatterers, we can, if we have the foresight to, we can put them in before able to do an early stage in the project. So these corner reflectors, they're just, some people call it, and that's going to ensure that wherever the radar wave hits on that on these three faces, it's going to return to the satellite with the same timing. So all of these signals are going to sum up constructively and gives a very strong and again stable measurement for this corner reflector. You can see on the right here, this is Imperial College. This is the Skempton building where we used to work pre-COVID. And you can see there's a lot of persistent scatterers being picked up, these dots, and they're mainly associated with corners on buildings or metal infrastructure on the roofs. These are quite typical. So in urban areas, you get a real wealth of persistent scatterers, whereas in rural areas where it's more on noisy vegetation, which isn't going to or growing or decaying, you're not going to get many persistent scatterers in rural areas in general. I'll just talk a little bit about the fact that because the satellite it's in circular orbit, it's going from south to north first, that's called ascending, and then north to south on the other side of the Earth. We've got these two different perspectives, essentially. The sensor is actually aimed, if you want to call it that, to the right of the satellite in the case of Sentinel-1. So as you're ascending, you get an eastward looking measurement, whereas when you're descending, you're getting a westward looking measurement. So this is important because we can use this diversity to do a bit of trigonometry and separate out the different components of any motion that we measure or any displacement that we measure. So essentially we're separating out any easting, westing movements, which I might call horizontal movement, things like that. In general, there's a lot more sources of vertical movements than east-west. For instance, seasonal changes in groundwater and shrink swell, anthropogenic tunneling activities might cause subsidence. And those are going to be distinct from east-west sources of movement, which really most commonly are only going to be slope movements, mass movements, and strike-slip tectonism. So by separating out these two components of motion, you can really get a better idea of what's causing the motion that we're observing in a set of InSAR results. So this is a bit of work by Tom Magan, who did just that on some. Before Sentinel-1, there was ENVISAT, which was also from the European Space Agency. Before that, there was another couple of satellites called ERS. And by looking at these long time series of data going back to 1992, I believe, was when the ERS was launched, you can look at long-term trends in the data. So the data from these satellites is a bit noisier, the separation between images is a bit longer, but you can still look at long-term trends. And by separating out these different components of motion, you can really start to see patterns in the behavior of different areas of the ground. So looking at these long-term data sets, you kind of end up averaging out and removing any, to a larger extent, seasonal effects. And as a result, Tom used this data from the InSAR, compared it with the topography of the chalk layer under the ground surface and the height of that layer, and used any essentially changes in height of the chalk to infer that there might be a fault there. And he found that changes in the topography, what he calls the subsurface topography of the chalk, corresponded really well to changes in behavior of the deformation that we've recorded via InSAR. So by using this along with borehole records, ground model that he developed, he could infer the presence of all these faults that he's plotted here. And yeah, these have been backed up by his ground model and a lot of borehole works. So as a result, we can really investigate near tectonism using the InSAR, or at least we can use that to help us investigate the location of faults that might be barriers to groundwater transport, and as a result might separate two areas of differential movement behavior. Just to say that Jenny Schooler also continued this work using Sentinel-1 data, and I don't know if I mentioned, we've got an article that she wrote that's coming out in Geoscientist magazine. So as most of you will be JOLSOC members, she'll go into a bit more detail on this in her article that she led the drafting of. So I won't dwell too much on her work, but she's also got some papers out on this, which continues the work of Tom in that respect of looking for faults in London that weren't previously identified by historical models. Then go on to Zishau's work, and this will show really clearly this identification and characterization of faults that we can achieve using the InSAR. And because he's looking at the Gobi Desert here, it's a very rocky desert. It's going to give us really amazing InSAR results in terms of there's no vegetation to muck up our results, to get in the way of things. So we get a really good coverage. And again, he's separated out the vertical and the horizontal motion, and been able to see quite clearly, especially I think in the easting deformation, there's very consistent patterns of deformation between these areas on the ground. And if you, as he's done, if you compare these to discontinuities in the optical data, you'll see that the differential behavior of the deformation measurements lines up really well with these discontinuities, which really implies that these faults are probably still active, considering that the moisture behavior in the Gobi Desert is obviously a lot more consistent and less variable as compared to somewhere more temperate like London. So yeah, I just feel like these look really clear in terms of the distinct behavior of these different blocks that he's separated out between faults. They line up really well with the optical data. And just to bring back a bit of engineering relevance for this was the site of a proposed rock laboratory for geological disposal of radioactive waste. So that's a very important piece of information to know that there's potentially near tectonic movements associated with nearby faults. If you're planning to build a facility that will dispose of radioactive waste, then you need to know how the area around it is evolving. Gosia Maida's work on the south coast of England. This is Cow Gap near Bournemouth, Eastbourne. And this is a nice rotational landslide. And it's, I think I've got a model here. Yeah, it's sliding along the gults here. And she's measured differential behavior of the toe of the slide as compared to the back scarp. So here is the The littoral platform is moving downwards with the rotational slide, whereas the toe at the other end is creeping upwards. I've got a few more examples of rotational slides. This was an MSci student, Bethany Grant. She looks at Folkestone Warren and observed similar behaviour of this rotational slide. The top of the cliff was moving downwards, but we could observe that there's a lot more lateral movements and potentially uplift of the toe here at Folkestone Warren. So Bethany encountered that there was a lot of vegetation in the area, which really masked the upper parts of the slope, but I'd say still got quite a lot of useful data in terms of how the foreshore was spreading out. Ventnor, so this was another master's student, William O'Connor, and he's hopefully publishing a paper on this soon. Again, we've got some differential behavior of the two ends of the rotational slide. We've got almost a rotational effect happening here, apparently in the data, because going by the ascending data, it's moving eastward, whereas it's moving upwards more so in the descending data. And looking at this differential behavior between these two distinct viewing geometries, we can really get a characterization of how the landslip is evolving. Moving on to my work. So as you might have quickly seen with Bethany's work, there was a bit of an issue in terms of vegetation covering the back of the slope, and that made it quite hard to see the wider extent of movement behavior of the, it's quite a big landslide. Folkestone Warren, you really want to characterize the whole thing, because the railway that's threatened on that slide is obviously quite small compared to the slide itself. So you really want to understand how the slide is varying. And to do that, you need more than just to pick out the persistent scatterers, you need to pick out all the vegetated areas as well, ideally. So this is a bit of work in South Wales. So here's the coverage that you get using persistent scatterer interferometry. So you can see the persistent scatterers, as you'd expect, they're in urban areas and the towns and the valleys. There's a few villages in the agricultural areas and farm buildings and pylons and such, but in general, we're going to get very limited coverage in the vegetated areas. And that's because there's a lot of terms that cause an error in your phase measurements that you need to filter out as part of the processing. But particularly hard is filtering out changes in phase that are associated with the actual scatterer itself. So for instance, this tree that I've animated, it's blowing in the wind, and every image you take of it is going to measure a different section of the tree. The orientation of the scattering element is going to change, so you're going to get a different measurement phase every time based on movement of this scatterer. Similarly, with the soil, most of the signal is going to reflect away from rather than back towards the satellite. So you're going to get quite a noisy measurement of the actual signal back from this soil here. You've also got to factor in things like soil moisture changes are going to differentially delay the signal. So you've got a real host of different factors that can affect your measurement phase from these natural materials. The idea then being, let's pick out all these different types of vegetation and see how they behave differently in order that we can then correct for them. So that's perhaps the core of the method that I've developed. What we find though is, this is crop map data from the Centre for Environment and Hydrology in Lancaster, I believe. And they publish crop maps of the UK based on different crops using their data and see how they behave differently in the InSAR phase. And we'll see consistent trends, in fact, for different crops associated with different patterns of growth and how they're going to obscure any underlying ground. What we did find though is that these maps are quite limited in terms of the scatterers are going to change between every image that we take every 6 days. So having an annual map of crops isn't going to quite have the temporal resolution in order to properly correct our data. It's never going to be this kind of, if you've got a crop class such as grass, that can cover a whole range of different scattering targets, different types of grass, different cuts of agricultural grass, different underlying soils. They're all going to behave differently from the radar's perspective. So we developed a sort of machine learning approach, basically, to use the radar data itself to distinguish different types of scatterer, and then use those, what we call clusters of different scattering of different vegetations, essentially, and use those rather than the crop maps, and found that they gave much better ability to characterize these quirky phase effects of different growing and decaying crops and different soils, which are going to have different responses to variable moisture contents over the year. So by picking out these different materials and these different behaviors in the radar data, we can correct for these. So that actually gave us a really noticeable improvement in coverage. So here's the persistent scatterers again, and you get a massive increase in coverage in terms of the vegetated areas when you correct for these factors. So I'll just quickly talk about some of the patterns in data that we see. There's this, I'm sorry to use this terminology, but a blue splodge. I like calling it a blue splodge of uplift. So that's associated, it's been observed in other InSAR studies of South Wales. That's been attributed to rebound associated with historical mining that's since ceased. The groundwater is then recovered in the area, and the hypothesis is that the area's rebound associated with this cessation of mining for coal. I'll actually zoom in on some of these features because you probably can't see them very well on this image, but the main thing that I want to convey is that by looking at these vegetative scatterers and trying to understand their behavior through the year, their seasonal behavior, we can really try and correct for this behavior and get a much better coverage of results. So I'll zoom in on this mine. I believe it's called Magan mine, and it was essentially abandoned when the company went bust. I want to say in 2010, somewhere around then, and it's been a bit of a hot potato ever since. But we can see that there's a very steep slope to the eastern end of the pit of spoil, and that's actually moving. Sorry, so the satellite here is going south to north. That's ascending, and it's looking east, which means that the blue here is implying that the scatterers are moving west. They're moving down slope towards the satellite, whereas the spoil at the top of the heap is settling and moving away from the satellite. So we can pick out these differential movements of the scatterers using this correction of non-PS. This is Fossiflan, land reclamation projects and open pit mining projects. So they were filling, I think they were excavating material and filling it back in quite quickly up until quite recently. I think it's continuing today, in fact, but you'll see this red area here, which is where they've recently backfilled the mine workings, and you can see that that's settling on the western edge of the pit here. We've got another blue area here, which is another slope movement towards the satellite, going material moving down slope from this quite large spoil heap here, whereas the rest of the spoil heaps are less steep slopes, and they're just settling mainly. Here's a debris slide in a place called Blaina near Abertillery. And again, the debris is moving down slope towards the satellite, and we've been in touch with the council on this one, and it's quite useful case study, I believe, this one, because they were aware of the movements, but they hadn't been able to access the slide for because of access requirements, it wasn't safe to access. So they were experimenting with a few different remote techniques, and we're very grateful for the remote data from InSAR, which confirmed some of their other data. Not much to say more on that one, I believe. So again, I've mainly presented data from one satellite, but rather than the separate east, west, and vertical components. But with this distributed scattering method, where we're trying to correct for the vegetation effects, we can still separate out the two different perspectives from the satellites. And so, for instance, we can see the debris slide here. It's moving away from the satellites in the descending data set. So the west-looking data set, it's moving away from the satellite. In the east-looking data set, it's moving towards the satellite. So we can still pick out these lateral movements and these vertical movements, such as from this landfill here on the west of the image. Moving on to the future, one thing that I feel is really untapped with InSAR and that we've looked into quite a bit is soil moisture monitoring. Now, there's a lot of techniques using the amplitude, which is the signal strength of the SAR data, in order to try and measure soil moisture. Essentially, the dielectric properties of the soil change with variable moisture content, and you get a brighter surface as the moisture increases. The trouble with using the brightness of the soil is that you've got vegetation growing above it, which is going to completely throw off your measurements of this amplitude. So using the diversity of both this amplitude and then the InSAR phase, which is also affected by the soil moisture, and then looking at a few other observables that we can use, which I haven't gone into too much detail on, but there's observables called the coherence and the closure phase, and polarimetric variables. We can use all these different data sources derived from the SAR images in order to try and counteract the effects of vegetation and really hone in on the moisture signal generated from in the SAR data. Being able to measure soil moisture has obviously got a whole range of applications, particularly in weather prediction, drought resilience, flood prediction. But probably more interesting for us, it's monitoring geohazards and the role that surface moisture has in controlling these slope movements and shrink swell hazards and other such hazards. So I haven't published this, and this will be nearer the end of my PhD when I publish this, but we've got some quite good correlations between the estimates that we've derived from the SAR data and what's been reported from independent data sets. So I think whether it's me at the end of my PhD or researchers in the future, which I think there's a huge scope for using this InSAR data to exploit in order to measure soil moisture. The beauty of InSAR is that the coverage is global, it's regular updates. So even if the resolution is never going to be really as good as what we can achieve from on boots on the ground methods, having that wide regional surveys of soil moisture will, I believe, in the future be extremely valuable. Also, just to mention, if we had to separate out the role of vegetation in detecting this soil moisture, then vice versa is also true. There's a lot of great correlations between the SAR data and different types of crop. These are probably less interesting to ground engineers, but it's worth noting that InSAR is also poised to be quite useful in crop monitoring, I believe, in the future. You find changes in terms of the scattering behavior, the objects, the vegetation. UAVs are going to be essential, and being able to really be flexible in terms of the wavelength of the signal that you use, the height and the angle, and the regularity of how often you measure, as well as the resolution. It's all going to be really aided by the use of a UAV. Using a drone, you can really change the parameters of your investigation rapidly with a drone. If you've got if you got an embankment that you believe is being particularly affected by moisture, surface moisture effects, then you can set up your drone in order to specifically investigate those and investigate how that's deforming your assets. So I believe UAVs are going to be really also the future in terms of InSAR monitoring. So yeah, no pressure to Anthony Carpenter, who's researching this at the moment. Yeah, a lightweight, portable. We're investigating software-defined radars and other miniaturizations of the data of the sensors. You can really combine this with a whole suite of different tools. So I believe photogrammetry on drones is really popular now and really powerful. There's no reason why you can't combine the two measurement techniques, and if anything, they'll really complement each other, I believe. So we've processed some data using data from one of our partners, and Ant's been working on the hardware and the design of the instruments on the UAV. That's just about concluding my presentation. Just should probably mention that I'm near the end of my PhD and I'm always looking for next steps. We've got a bit of a consultancy in case you want to, in case you have a project that you're interested in about. But if you just want to learn more, then I'll be very happy to talk after the meeting. Hopefully there'll be time for questions if I haven't rattled on for too long. So yeah, thank you very much. I'll just do some conclusions. InSAR's got a wide range of different phenomena that it can investigate. It's not just infrastructure monitoring, which you might already have been aware of, but it's also geological phenomena and geotechnical phenomena. Rural areas have been prohibitively noisy in the past, especially for persistent scatterer techniques, but using advanced processing techniques such as my own and other ones which I didn't really cover in enough detail, unfortunately, such as SERG or intermittent SPAS. There's different techniques out there that will give you different results in rural areas, so just because it's a rural area doesn't mean it's prohibitive in terms of getting a good result out from InSAR. I think ongoing work into drone-mounted SAR sensors is going to be a game changer in terms of really any asset that you have that's on the surface, it can be monitored with a drone quite readily. And the global nature of the data from satellites is still going to be extremely useful in terms of offering this global monitoring of deformation phenomena, as well as soil moisture changes and vegetation phenomena. Jenny, my colleague, and the supervisors are really leading on this. They're writing out guidelines for monitoring civil infrastructure using persistent scatterers, and that's going to be a SERG guide. So I'd just like to mention that as well, which should hopefully be published in time. And I've just got some references that I'd like to flash up there. So thank you very much, and I hope I haven't spoken for too long. I'll just see what the time is. Okay, 40 minutes, perfect.
That's spot on.
Thank you very much.
Thanks, Stuart. So if you've got any questions, you can either type them in the chat box or, of course, unmute yourself and ask away. I should mention that this is also a joint engineering group presentation. Sorry, I didn't mention that at the beginning. Do you have any questions?
Yeah, could I ask a question? Colin Warren.
Go ahead.
Yeah, I'm interested in terms of, you showed the Northern Line extension. I mean, there's a lot of changes in moving materials around and building box structures. I mean, how do you make sure that you're not looking at differences due to that type of work?
It's I think especially the east-west components, you're not really going to see a lot of anthropological sources of I don't believe of movement that are going to give you a consistent east-west component over a wide area. So I don't want to, so this is mainly Jenny's work. I don't want to preempt her work, but I'd say that she'd probably argue that it's because you've got a whole region moving from east to west. That would imply that it's more to do with the underlying rock or the underlying soil, rather than anthropological effects.
Thank you for that. Any other questions? Be dead silence now.
I could ask another question of Tom.
Sure, yeah. Was that a good answer? Was that okay?
Yeah, I think so. I mean, I know there's tunnels there, so as long as the trend is in the tunnels, then you're generally okay.
Yeah.
So, but I mean, there's also Tom Morgan, you know, in terms of the structural type of faults and stuff. I mean, is it backed up by the lithostrat? I mean, has it got a lot of lithostrat in the chalk in terms of choosing, you know, checking out the faulting? Because a lot of those projects have got lithostrat associated with them in the boreholes. I
think he's analysed. I'm tempted to he's on the call actually. I'm tempted to throw him on. Is that?
Hi, Stu. Hi, Colin.
Yeah. Hi, Tom. Yeah.
So I've done some geological modelling in East London, and I validated the faulting there. I've also compared it with BGS lithoframe faulting, and that's shown good validation. There are some faults which aren't picked up by it, which aren't near my model either, which I haven't been able to validate. But just the overall, given how all the others have been validated, it gives us a bit of confidence that they are, even the unverified ones, are likely faults as well. It's something for future work though, definitely, to look at ground truthing those. So I think some of them it's going to be difficult, because I think some of them appear to be more strike slip based faulting, and being able to model those is going to be a challenge for sure.
Yeah. Okay.
I think from the InSAR perspective, there's it's quite a limited amount of things that you can measure, and being able to in urban areas. When you've got a persistent scatterer, if you can measure the signal amplitude in order to show that it's not changing what it is, it's not changing its orientation, its geometry, then you really only, it could be a lot of different sources of movement, but in terms of whether it's moving or not, when you've got persistent scatterers, I think you can really rely on the data if we've got enough images to characterize the error sources, which is something we can do. So I'll defer to Tom on being able to understand what's actually causing the movement. But I think once you've got a long enough time series of, especially the Sentinel-1 data, which is really regularly updated, I want to argue that that's quite reliable indicator of movement when you're looking at urban areas.
Could I ask a question?
Of course.
Thank you. Mark Davis here. Stewart, the system, does it pick up railway lines easily?
It's quite tricky. It depends on the orientation of the lines, essentially. Depending on which way the lines are orientated compared to the satellites itself, they can either hit the line and bounce off into the void of the universe, or they can bounce straight back to the satellite and give you a really good strong signal. So north-south orientated railway lines are quite reliably picked up, but yeah, east-west ones, you don't get a very good signal generally. You normally pick up the power lines and such associated with railways and the associated infrastructure. They come up quite nicely in the data, but I'd argue this is a good driver for the UAVs in order to be able to not worry about the orientation of what you're looking at, just to be able to see them clearly. With higher resolution satellites, which you pay a bit more money for, you don't pay for the Sentinel-1 data, but you pay quite a lot of money for the high resolution satellites. Things like railway lines will come up quite a lot better.
Okay, thanks.
Thank you.
Do we have any other questions? Oh, I think that might be it. Okay, then I'd like to give Stewart a virtual round of applause. Thank you for stepping in. It was a really interesting talk, and we had a good turnout again. So up about 53 people today.
Thank you. Thanks
so
for
that's
coming.
really good. Yeah, if you want to do any more presentations, please do let us know.
And if you've got any more questions, please just give us an email. You might also know Tom and James, who are quite regular, I believe, in these meetings. So feel free to get in touch with any of us. We love to talk about our work. So yeah, thank you for listening. Cheers.
Fab, thank you. So just while everybody is still on the line, our next talk will be given on the 15th of June, and that's by Martin Wells from BP. Thank you all for coming.